But now we're moving on to a new unit. This third unit is going to be rotational things, and there's 3 chapters to it. Number 9 here is rotational motion, so this sets the basis. And then chapter 10 is simple machines, many of which work on a rotational basis. And then finally, universal gravitation, which we'll touch a little bit on examples this chapter, a lot more on examples when we get to chapter 11 of how gravity often causes things to go in circles. So rotational motion, clearly you can see this windmill is spinning in a circle, so we need to talk about this. It's a very common type of motion in our world, although it's not what Newton's first law would have told us, right? Newton's first law said objects in motion tend to stay in straight line motion. So rotational motion does not just happen. If something is going in a circle, it is always because there is a force acting on it, pulling it toward the center, as we will learn. But we see lots of circular motion in our world. Our planets go around the sun, the moon goes around the earth. Even when we throw a ball, it follows an arc that is circular to some degree. So this comes up a lot. So we need to talk about it, we need to learn about it, we need to understand what the requirements are for this to occur, and to be able to describe the motion and predict the motion like we can for linear motion after chapters 4 through 8. So we've got, I got this little animated satellite flying around the Earth, and again, it goes in a circle because the Earth's gravity is pulling the satellite inward. And that is what allows it to continually go around the Earth. If the Earth suddenly disappeared, if the Earth's gravity suddenly disappeared, this object would not go in a circle. It would, just like the rock in the video we watched about inertia, it would take off and go in a straight line and just keep going straight forever until there was some other force that affected it. So the first thing we have is we have 2 different words to describe things going in a circle. There's the word rotation and there's the word revolution. And again, as I've mentioned many times in this class, physics is great because it's very real and very practical in our lives, and it's a little challenging because a lot of the language of physics is used in our everyday lives and not very carefully. So many people use rotation and revolution interchangeably, but there is a difference between the 2. And that's what we're going to tease out here on this slide. Rotation is when you are spinning, going in circles, but around an axis that is located within the body. So a common example of that is figure skating, right? When they go into one of those axles, one of those spins, the axis is passing right through their body. And then, of course, the Earth is rotating on its axis, right? There's an invisible axis passing from the North to South Pole, and the Earth rotates around that axis. If you sat on a spinny chair and spun around, you would be rotating. And that is contrasted with the idea of revolution. You're still turning in a circle in a revolution, but you're going around an axis that is external to you. So it's still about circles. Both of them are about circles. In the one case, rotation, the center of the circle is inside of you or the object that's spinning. In the second case, the center of the circle is outside of the object that is spinning. So if you would think of the people on the roller coaster, right? They are going in a circle and they are going around this pink dot here in the middle. And so that pink dot is outside of them. And then, of course, our favorite example, the Earth, is doing both things, right? It is rotating on its axis, but then it revolves. It goes around the sun, revolves around the sun. So rotation and revolution, we want to be able to make that distinction and understand the difference between those 2. So here we show the blue dot that all the riders are outside of. Now you could very, very justifiably make the case that the Ferris wheel itself is rotating because that dot is within the Ferris wheel, but the riders are revolving, okay? And the same thing is true of us on Earth. We are revolving around the axis of the Earth, unless we're Santa Claus and we live on the North Pole, but the Earth itself is rotating on that axis. A lot of animations in this particular presentation because circular stuff lends itself to that. You want to see the motion in a circle to understand. So now we're going to go through a series of connections between what we've already done and what we're going to do. And I'm going to post on Blackboard, and I don't think I can really post it to YouTube, but a document that just is a chart that shows these relationships, because we're going to connect linear things that we've already done with rotational things. So for example, this is arc length. Arc length is the distance along the arc, right? So this green line would be an arc length. We could take a piece of string, we could stretch it out along the green line, we could straighten it out, and we could measure it with a meter stick. It would be a distance, an actual linear distance. Or you can think of walking a section of the earth, right? You would walk a distance, or you drive a distance, and your odometer would tell you what distance you've traveled along that curve. So that arc length is a linear distance. But if instead we look at it from the circle's perspective and we say, well, that blue angle is so many degrees of our way around the circle. Well, that would be a angular distance. How many degrees or how many radians have we moved around the circle? And you can say, okay, fine. So we got arc length green for linear, and we've got theta for angular. What's the big deal? Well, the big deal is, of course, that they're connected. They're related by a very simple mathematical relationship, and that involves the radius. So the theta that we get is the arc length divided by the radius, or if you rearrange it, it's r times theta equals the arc length, which is how it's written over here. So we are familiar with that from our time in geometry, for some of us longer ago than others. The distance around the whole circle we call the circumference, okay? The circumference, C, is the distance all the way around. Imagine there's red underneath that green. The distance all the way around is the circumference, and if we take our circumference and we divide it by the radius, well, our equation for circumference was 2 pi r. So if we divide by the radius, we get left with 2 pi. So an angle going all the way around the circle, or 360 degrees, is an angle of 2 pi radians. And we like to use radians in physics simply because it doesn't require the conversions that degrees will require. And we'll talk about on the next slide the connection between degrees and radians. But we're gonna use theta in radians in this chapter, just because it makes everything work out a lot nicer, right? If we've got an arc length here, say 5 meters, and we divide it by a radius of 2 meters, 5 meters divided by 2 meters, we get 2.5, but the meters cancel out. And that leaves us with units of radians, not with units of degrees. So we can do our math very directly if our angle is in radians and our subsequent values are in radians. So again, if you haven't already, look at that chart, maybe download that chart from Blackboard and print it out, or have it in front of you while you watch this video and go through these notes, because that chart is really going to help you understand all these relationships. And the very first one at the top is rotational displacement is theta, and linear displacement is arc length. So we've got, this is the rotational version of distance. So yes, one full circle is 360 degrees, and one full circle is 2 pi radians. So theta can be 2 pi radians, or theta can be 360 degrees. So that means 2 pi is 360, that means pi is 180. So if you want to convert from one to the other, you either need to multiply by pi over 180 if you're going from degrees to radians, or multiply by 180 over pi if you're going from radians to degrees. So we moved from displacement to velocity, and that's where we're going to move here rotationally as well. We talked about distance, and then we talked about velocity, how fast you cover distance. Same thing here. Now we're going to move to rotational velocity, or angular velocity. Both words are used to describe it. It's represented by the Greek letter omega. You might have noticed a pattern already. Linearly, we call distance or displacement d or s, English letters. Rotationally, we called displacement theta, which is a Greek letter. Now we get to velocity. Linearly, it's v for velocity. Rotationally, it's omega for angular velocity. So most of the angular things are represented with Greek letters instead of English letters that just helps us keep the two ideas separate. Rotational motion is a little tricky. There's a couple of different ways to think about it. Really, there's not. There's really one way, but when we think of linear velocity in a rotational setting, it can cause some confusion. So the number of rotations per time, RPMs or RPSs, we're familiar with that from our car, right? It tells us how many RPMs, that's actually the RPMs of the engine, not of the wheels, but how many times the crankcase or the crankshaft is spinning. And we know that if we get spinning too fast, that's bad. That's why that section's in red. But this is not the most useful way for us to do problems in physics necessarily. So we have this expression, right? Just as we had v equals distance over time, now we've got omega equals theta over time, the same relationship. So we could say revolutions or rotations per time, right? We could say we went around the circle 5 times in a second, so that's 5 revolutions per second. That would be okay, but when we want to discuss this in terms of theta, theta is often going to be expressed in radians. So 5 times around the circle would be 5 times 2 pi. That would be 10 pi radians divided by a second. So our omega would be 10 pi radians per second. Both are okay, but one of them is going to be more useful to use as we go on and try to use it in a problem. So here we have just a little bit of an animation here showing that, you know, in each unit of time, we color in another part of the circle. So our theta is getting bigger and bigger, right? This would be just like if you were running along the ground and you ran 2 meters in the first second and 3 meters in the second second and 4 meters in the third second. Your total distance covered would keep increasing even if your velocity was not increasing at that rate. And this circle is being colored in a faster and faster omega, right? It's covering more of the circle each unit of time than it covered before. And of course, we're going to get to that in a moment, the idea of acceleration. But you don't have to have acceleration just to understand that angular velocity, omega, is theta over time. And then we get to the idea of relating angular speed to linear speed, right? Linear speed was just the distance divided by the time. And so we're going to have this relationship between omega and velocity. And this becomes extremely, extremely important because, of course, as you move in or out on a circle, your radius changes. As your radius changes, the distance all the way around that circle changes, right? It's 2 pi r. So the bigger the circle, right? If you've got a little circle, you're going to have a little circumference. That doesn't work. If I get closer to the camera, it gets bigger. But then as you move out, you have a larger circumference. It's 2 pi r. So although the whole object might be spinning and is probably spinning with the same angular speed, as you move out from the center of the circle, the linear speed going around that outside circle gets bigger because you got to get all the way around the circle in the same amount of time. So we have this relationship, omega times r equals v. And that's the very same relationship we had for displacement, right? It was theta times r equaled arc length, okay? Or it was arc length divided by radius equals theta. Here it's velocity divided by radius equals omega. If you ever get confused when to divide and when not to divide, or when to divide, when to multiply, I would encourage you to think in terms of units. Think in terms of units, okay? Velocity needs to have distance divided by time. And so if you do radians divided by time times distance, the distance times the radians become meters. Meters over time is what we need for velocity, okay? And it really shows up when you try to do it the wrong way, right? If you do omega divided by radius to get velocity, you would end up with something divided by meter seconds for your units, and that would not be correct. This makes more sense with a picture, and we'll have that here on the next slide. So here we go. So we've got this rigid object. You can see, for example, a record player. Here you can see it spinning, right? We know the records run at different speeds if you're familiar with records. Some of you are young enough to not be familiar with records, but the record players had 3 settings, at 33 1/3 RPM, 45 RPM, and 78 RPM. And those were all omegas. Those were all angular speeds, how many rotations per minute the record was going to do. But when you actually make a record, you have to take that into account, the fact that the needle is going to be going over the groove much quicker around the outside and much slower around the inside. Maybe I said that backwards. The point is that the linear speed is different. No, I did not say that backwards. The linear speed is different, and at a greater radius, you're going to have a greater linear speed. And so how you actually put the bumps in the groove that the needle hits and plays the music is going to be different closer to the center than it is at the edge. And here's just a very simple model of 2 points on a rigid object, A and B. And they're going to end up with different velocities. A is going to have a greater linear velocity as it moves and covers distance in a certain unit of time than B is. And if you just think about it, whether you think about the whole circle or whether you think about a quarter of a circle, right? For him to go to a quarter of a circle, he's got to cover that much distance. For B to go a quarter of a circle, he's only going to cover that much distance. But they're both going to do it in the same time. So if you do a greater distance in the same time, then you've got to be faster, right? This goes back to our discussion of the track and the fact that the outer lanes of the track are longer and the inner lanes are shorter. So we're going to look here at the math of that equation that we just gave. We're going to throw some numbers on here. So say B has a radius of 1.2 meters and A has a radius of 2.5 meters, and the whole object is spinning. I had it spinning the wrong way relative to the arrow. The whole thing is spinning with an angular velocity of 5 radians per second. Okay, so it's going 5 radians per second around. That's almost a full circle per second. And we have these 2 different radiuses for A and B. So what we see is that for B, it's going to be omega r equals the velocity, linear velocity of B. So omega is 5, the radius is 1.2, so we multiply those together, we get 6 meters per second. So the linear velocity of B, the distance it's covering per time as it goes around the circle, is 6 meters per second. But for A, at his greater radius, it's going to be omega times the radius of A equals the velocity of A. Okay, same equation, just plugging in the values for B versus the values for A. So it's 5 radians times 2.5, so it's 12.5 meters per second instead of 6 meters per second. So you're covering a greater distance in the same amount of time. I just really like going clockwise. That's all there is to it, even when the arrow tells me it's counterclockwise. So we can think about that with the world, right? We can think about different people at different places on the world. We know the world is a sphere, and it's spinning through an axis that passes from the north to the south pole. So the people at the equator in the middle, they're going around the biggest circle. They have the biggest distance to go, right? You can imagine the Earth like this example if you were looking down on the North Pole, right? As you look down on the North Pole, there would be the people close to the equator that would be out toward the edge of the circle you saw, and the people halfway between the equator and the North Pole would be at like point B, and they would have a smaller, now we want to be careful, everybody on the Earth has the same radius, right? The same distance to the center of the Earth. Same distance to the center of the Earth, but the distance to the center of the Earth is not what matters here. What matters here is your distance to the axis. So this guy, although he has the same radius to the center of the Earth as the guy at Ecuador, he has a much shorter radius to the axis. Okay, so then you can see that the circle he's going to go around is smaller than the circle this person's going to go around. And yeah, I shouldn't draw on the screen. That's all there is to it. So the people at the equator with a radius of 6,400 kilometers, they are going a very great distance. They are going 25,000 miles a day as they go around the Earth, even if they're not moving, even if they spend the whole day in bed like I did when I had my back issues. They go 25,000 miles in one day, even if they're laying on their back all day. So they're going over 1,000 miles an hour just because they live at the equator or near the equator. On the other hand, here in Lower Canada, you're going around a much smaller circle, so your velocity, your linear velocity is smaller. Now we know everybody's angular velocity is the same, right? Everybody completes one full rotation in a day, one rotation per day, one RPD, but different linear velocities because we're going around a different size circle. And of course, you know, Santa Claus up here on the North Pole, he is going very slow, right? Very slow because his circle is very small. Obviously, there actually is land at the South Pole. I was listening to a researcher once who had spent a season at the South Pole, and they were talking about their daily routine. And they said every day they'd get up, and before breakfast, they'd run around the world. Sometimes they'd run around the world a couple of times. Because if you live at the South Pole, running around the world is as simple as running around the flagpole or whatever it is that marks the South Pole, because you're so close to the axis that your circle is very, very small. So that is the difference between linear and angular speed. This is the relationship, the mathematical relationship. That's an important idea. In the northern hemisphere, the further south you are, the greater your linear speed. In the southern hemisphere, the further north you are, the greater your linear speed, because you're getting toward the fat part of the Earth, essentially, which gives you a bigger circle to go around in the same time. I don't feel like I can say that enough. Bigger distance in the same time means you have to go faster. And if the object is rigid, then you're going to be forced to complete the circle in the same amount of time. Now, if the object is not rigid, then things are different, but that's not what we're discussing right now. So we did distance, displacement, we did velocity, now we're going to do acceleration. So again, that was the same order we went in chapter 4, displacement, velocity, acceleration. Same order we're going in here. And just like before, acceleration was change in velocity divided by change in time. We're going to do change in angular velocity divided by change in time to get angular acceleration, which is alpha. Okay, so angular acceleration is alpha instead of A. Kind of nice, right? A is the first letter in the English alphabet. Alpha is the first letter in the Greek alphabet. Alpha is the change in omega divided by the change in time. But it has that very same relationship that we had for theta and omega for displacement and velocity. It's this same relationship involving the r, and it's angular times r equals linear, or linear divided by r equals angular. So really important relationship in all three areas: displacement, velocity, and acceleration. It's maybe the most important in velocity, but it's important in all three to be able to connect from one to the other. And here we have this same animation, but you see we only covered one pi slice and then 3 pi slices, and it gets progressively larger because we have a non-zero angular acceleration. So our rate at which we're turning around the circle is going up. This is a small angle, that's a bigger angle, an even bigger angle, an even bigger angle. Oh, wow, I managed to stop it. Keep my fingers away from it and maybe it'll go normal. So non-zero alpha means that we're accelerating. We're covering distance quicker and quicker, and this is angular distance, which means we're going around the circle quicker and quicker. And again, examples of this that are maybe meaningful to us, you can think of somebody riding a bike and the bicycle wheels turn faster and faster. So as you pedal, you're going to have a positive alpha, and that's going to speed up the wheels, which ultimately is going to speed up your linear motion too, but you can see the wheels spinning faster and faster. Or you can think again of a car and either the engine spinning and watching your RPMs go up, or the wheels on a car spinning, or a vehicle spinning as somebody increases the velocity. Because if you're in a wheeled vehicle, in order for your linear velocity to increase, your angular velocity has to increase too, because that wheel has to turn in order to move you down the road. So now we're going to move on from displacement and velocity and acceleration to a bunch of the other principles that we learned about linearly. So after we did our chapter on describing motion, chapter 4, where we did velocity and acceleration and displacement, we moved on to chapter 5, which was about Newton's 3 laws, and the idea that Newton's 3 laws connect motion to this idea of inertia, right? Those Newton's laws of motion. The first one was the law of inertia, and the second one, F equals ma, depended on the mass as well. So rotationally, we have something called rotational inertia, and it's analogous to the linear inertia. Now, the linear inertia was really easy because it was just mass. If you got more mass, you got more inertia. If you got double the mass, you got double the inertia, so on and so forth. Rotational inertia is more complicated, okay? Capital letter I that we use, which is a little challenging because sometimes it just looks like a 1. But capital I, it depends on the mass. It totally does. It's rotational inertia. But it also depends on how close you put that mass to the center of your rotation, okay? So here's a very simple example, right? I got these two disks. They're about the same thickness. They're the same radius. You can imagine they have the same mass. If we were in class, I would have two, and we would physically do this example, but instead we get to look at the pictures. So this one, the mass is distributed throughout evenly. We call this shape a disc or a cylinder. The mass is spread out. This one, the mass is all around the edge, all around the rim. Okay, so we call this a hoop because all the mass is out here around the edge. Think of a hula hoop, right? Hula hoop's got a big hole in the middle, all the mass around the edge. And although these things look similar in a lot of ways, they do not have the same rotational inertia because here the mass is further from the center, and therefore it's going to be harder to get it turning and harder to stop it from turning. And if you remember our discussion of inertia, the inertia is the resistance to change in your motion, right? So if you're harder to get moving and harder to stop moving, then you're going to have more inertia. So yes, how much mass you have matters, but if the mass is further from the center, you're going to have more resistance to change. If the mass is close to the center, you'll have less resistance to change. Again, there's an excellent video done by this Julius Miller. I put a link in the description of this video, or you can just type Julius Miller and type rolling things into your YouTube search and you'll find it. It's a 15-minute video. He talks a lot about discs and hoops and spheres and different shapes and some of the ideas, and does a lot of examples of why this is the way that it is. So I would strongly recommend you watching that video since I can't show you the demonstrations in class because we're not here. So here we just have a chart. I just stuck a chart in here of the moments of inertia of a lot of different objects. And really these first three are the only ones we're going to spend very much time on in this class. So again, the hoop, the mass is further away from the center. So the moment of inertia is bigger. And it's equal to m and then the radius squared. Now you might say, well, how is that bigger? Well, compare it to the solid cylinder where the mass is distributed all the way through. Some of it is close to that axis. Well, that's only 1/2 mr squared. So we see the hoop has twice the moment of inertia as the disk does, okay? And when you think of a disk, you go, well, how could I get the mass even closer to that line? I mean, we've got the object filled in already. How can we do it? Well, the ends of the disk are just cut flat, right? You can think of a penny or a nickel or a coin, right? The ends are just flat, and you've got curvature in the middle, but the ends are flat. So if you took some of the stuff around the edge and you stuck it on either end, that would put that mass closer to the axis, right? And if you did that and you did that perfectly, you'd keep scraping it off the outer edge and you'd keep piling it on the ends, and eventually you would end up with a sphere. You would end up with a perfect sphere. So you notice the sphere has an even lower moment of inertia than the disk does, right? 2/5 is a little bit less than 1/2. And this is, in fact, one of the lowest ones for a symmetric circular type shape that you can get. And it's actually why we believe stars and planets and moons and all of those things are spherical, because they're spinning. And as we'll talk about a little later, spinning has a lot to do with your rotational inertia. And this is the best shape to get in to have your moment of inertia as small as possible. Sometimes we call it rotational inertia. Sometimes we call it the moment of inertia. It has nothing to do with time. We just call it the moment for other engineering reasons. So you've got those three that you really need to know, that the sphere is the lowest because the mass is closest to the center. The hoop is the highest because the mass is far away from the center. And then you can think of a thin spherical shell, right? It's a sphere, but it's hollow, right? Think of a volleyball or a basketball or something like that. So this fraction is quite a bit higher, right? 2/3 instead of 2/5. It's actually higher than the disk because the mass is all around the outside, okay? Because it's a hollow sphere shell. A shell has space inside of it. So, and then we have some other ones. We don't really, these don't come up very much, but the rod comes up a little bit. So if you've got a thin, long rod, if you rotate it around the center, you'll get a lower moment of inertia because the mass is pretty close to the center. Whereas if you try to rotate it around the end, you'll get a higher moment of inertia. So 1/12 is a lot less than 1/3. And you can do this with your writing utensil, with your pencil, right? Take your pencil or your pen, put your fingers right in the middle of it, and I'm going to make my screen bigger here for a moment. Put your fingers right in the middle of it, like this, and wobble it back and forth. And you'll find it's pretty easy to do if your fingers are in the middle, but then you pull the pen to one end and you do the same thing, and you find that it's harder. It's harder, especially when you switch back and forth. You realize, wow, yeah, it is. It's a lot harder to do the end than it is to do the middle because the mass is further away on average from the point of rotation. And that's what this is all about. It's not always necessarily about the center. It's about that red line. Where are we rotating around? And if we take that red line and it's through the center, that's fine. But if we take that red line and we put it somewhere other than the center, then that's going to make our moment of inertia go up. Maybe spend too much time on that. So we move on to other things that we learned, right? Chapter 5, we learned about forces and Newton's 3 laws. So Newton's second law was F equals ma. So what's the rotational version of F equals ma? Well, we already mentioned when we did chapter 7 about torque and balancing torques, we said torque causes a rotation the way force causes an acceleration. So torque is the rotational version of force. So torque T, rotational version of force. A moment of inertia, I, or rotational inertia, I, is the rotational version of inertia, which is mass. And then alpha is the rotational version of acceleration. So torque equals I alpha is really just F equals ma, but for things going in a circle, right? And you can think, if you've got some kind of ball or disc or something that you want to start turning or stop turning, it's going to be a similar situation, right? A force is necessary to get it spinning, and a force is necessary to stop it from spinning. Then we moved on to chapter 6, which was momentum, right? And we said momentum, rho was mv, the inertia times the velocity. Those were the two things we put together. So angular momentum, similar idea. We're going to use rotational inertia, I, instead of m, and we're going to use rotational velocity instead of linear velocity, v, okay? So we're seeing a lot of equations here, but a lot of these simply mirror what we've done already. And again, that chart is going to be really helpful for that. Now, angular momentum is represented by the capital letter, English letter L. I don't know why exactly they switched back. Torque is usually the Greek letter tau. I couldn't get a capital tau to show up here, so I used a capital T. But this is the one that switches out of Greek and goes back to, well, I guess rotational inertia isn't really Greek either, it's I. And then the second part of our momentum discussion was this idea of impulse, right? Impulse equals change in momentum, Ft equals m delta v. So we look at the angular version of that. Angular force is torque. Angular time is, well, it's still time. Time doesn't change. Isn't that nice? There's something that doesn't change for us. Mass becomes rotational inertia, and then change in velocity becomes change in angular velocity. So this is the rotational version of the impulse momentum theorem. Tt equals I delta omega. A little confusing to have TT, right? But one of those T's is torque and one of those T's is time. So just a little application here of angular momentum. Just like linear momentum, it's conserved, but it's a little more interesting. Linear momentum was a little boring because it was just momentum equals mv. And we've got momentum, which is conserved, which means you can't create any or destroy any. And you've got mass, which is conserved. Learn that in chemistry, reinforce that in physics. Can't create or destroy mass. So when you've got only 3 variables involved and 2 of them are conserved quantities, it's pretty boring to see something just moving along in a straight line with momentum, right? Because as it moves along, its mass can't change, and as it moves along, its momentum can't change. And so if 2 of the 3 things aren't changing, then the velocity doesn't change either. And so for linear momentum, things only got interesting when we started crashing things into each other, and then the momentum could be transferred from one object to another, and the collisions were interesting. Or we applied a force, right? Like the baseball bat hitting the baseball. We applied a force and that changed the momentum. But just looking at the object itself, momentum was kind of boring. Okay? Rotationally, it gets more interesting because we have L equals I omega. Well, again, angular momentum is still conserved. Still conserved. So this part doesn't change. The left side doesn't change in terms of conserved. But the I becomes more interesting, right? Because the I has an M part and it has an R part, whether it's MR squared or whether it's 1/2 MR squared. The point is there's an M and an R. So we can write this equation generally as L equals MRV. Now, maybe one of those is squared. Maybe there's a coefficient. But in terms of the variables, these are the 3 things. Well, momentum and mass are still conserved, but now we have 2 other variables which aren't conserved, and so we can see something interesting happening without a collision. So for example, you've got a figure skater here, right? And she's spinning around and her arms are out, and then she brings her arms in close to her body. Well, she has basically reduced the average radius of her mass. So as her radius goes down, that makes her moment of inertia go down, and as her moment of inertia goes down, her angular velocity can go up. And so she spins faster, right? And whether you've done this as an ice skater or not, you've probably done this on a spinny chair, right? Put your arms out and you spin, and then you bring your arms in, and you will spin faster, especially if you have some mass in those on the ends of those arms. Again, if we'd had class, I would have sat in a spinny chair with the textbook in each hand and spun and pulled the textbook in, and you would have seen that I spun faster. So the moment of inertia was large, and so the rotation was slow, but that product has to equal the same angular momentum. But when she brings her arms in, her moment of inertia goes down, and so her angular velocity goes up. And of course, that's part of figure skating, right? When you jump in the air and you want to do a triple axel, you have to make yourself very, very tight, very small, so you can spin really fast and get through all 3 rotations before you come back down on the ice. And the same thing happens for a diver, right? Trying to do so many somersaults before they hit the water. They're not spinning around a vertical axis the way the Earth is or the ice skater is. They're spinning around a horizontal axis, right? They want to rotate this way around an axis in the center of their body. And so when they're stretched out like this, they have a large moment of inertia. Their feet and their hands are far away from their center. And so they're going to rotate slowly. But when they ball themselves up, they can spin very, very quickly because they have a smaller I, again, smaller I, higher omega. So that's true in diving, it's true in gymnastics, it's true in a lot of different sports. You can see this principle come to bear, and this is what I was talking about in terms of the planets, right? If you've got an object in space that has congealed out of some smaller objects that stuck together, if they would form themselves into a sphere, then they would have the smallest possible I, and they could spin faster. And we see that amongst other places when a star collapses the collapsed star ends up spinning very, very fast because the radius has gotten very small. And we have these neutron stars that have as much mass as our sun, but are only a couple of dozen kilometers across, and so they are spinning super fast, going around once or twice a second. And that's very surprising to us, and it produces unusual light effects that it took us a while to identify as coming from something stellar. So that is the first half of chapter 9. Again, we've basically gone through and we've discussed all the angular equivalents of the linear things that we learned in our first 7 chapters or so, which can kind of seem like a lot. I realize that, and as you get to the homework, you will find there's kind of a lot of different problems that you have to do. But again, that chart is very, very helpful. There's also another link I'm putting in the video description to a series of videos by something called Flipping Physics, and they do a great job of explaining it. You know, he has a series of these videos. Each one is only a few minutes long, so you could click on this link and say, hey, I still don't quite understand the angular acceleration part, and you can go and click on his angular acceleration video and just watch that part, or you can watch the whole series. It's really helpful. He does a great job of explaining it, I think. So that's the end of this particular video. There'll be a second one on chapter 9 where we'll cover the second half in a little bit.